Welcome to the problem section for trigonometric equations involving multiple angles. And it says for the first few problems, find all solutions for theta between 0 degrees and 360 degrees, and then verify your answers graphically. So for the first one, of course, taking the inverse sine of square root of 3 over 2 is going to give us 60 degrees as a reference angle. But before we check into that, let me point out the following, that if our solutions for theta are supposed to be up to 360 degrees, then when we take the inverse sine for the 2 theta, we could go all the way up to 720 degrees. Why? Because once we have divided this here by 2, so we just have theta, and then that goes up to 720 over 2, which of course is 360. So keep that in mind as we determine the angles here, that we should go all the way up to 720 degrees. Reference angle, as I had already mentioned, is 60 degrees. And then the other positive solution is in the second quadrant, so we have 120 degrees. And then we go beyond 360 degrees, so 60 plus 360 is 420 degrees. And then 120 plus 360 is 480 degrees. So these are all the solutions. I'm going to copy that degree sign in here. And then we divide by the 2, so we're going to come up with 30, 60, 210, and 240 degrees. Just as we had said, once we plug in the 30 degrees here, sine of 2 times 30 is sine of 60, which of course is this, square root of 3 over 2. Or if we plug in 240 degrees, then we have sine of 2 times 240, sine of 480, which is the same as sine of 120, which is square root of 3 over 2. So all these solutions check. Okay, the next one. Again, we're going to have 2 theta. And again, we may go all the way up to 720. So again, keep that in mind. Well, the reference angle, of course, is 45 degrees when we take the inverse tangent. And with the negative, we need to be in the second and the fourth quadrant for the tangent. So we're going to be at 135 degrees. And we're going to be at 315 degrees. And we're going to be at 495 degrees. And we're going to be at, so it's adding 360 to this one here, and then 360 to this one is 675 degrees, and that would be it then. And then we divide by the 2 in the front here, so we come up with these 67.5 degrees. And this one is 157.5. And this one here is 247.5. And this one here is 337.5. I'm going to check solution manual to make sure that I'm able to divide by 2 in my head. Yep, that looks correct. Okay, and all these solutions check for the same reason that we talked about earlier. Let's go to the third example here, third problem. So cosine 3 theta equals -1. Well, only one of them will work, which is 180 degrees. So keep that in mind. However, with the 3 theta here and the theta going all the way up to 360, we could go up all the way to 1080 degrees. So again, keep that in mind. So we're going to have 180 degrees, and then we're going to have 540 degrees, 360 degrees more, and we're going to have 900 degrees for 3 theta. Then we divide by the 3. So we have 60, 180, and 300 degrees. And again, you can plug them in here. For example, when you plug in 180 degrees, you have 3 times 180 is 540. Reference angle is 180. Cosine 180, of course, is -1. And when you plug in this one here, 300 degrees, cosine of 900 degrees, reference angle is 180. And again, of course, cosine 180 is -1. Let's go to the graphing calculator and check these 3 problems. Okay. So the first one was, let's get rid of the previous one, sine 2 theta. And then, of course, I subtract square root of 3 over 2. So I can easily look at the x-intercepts. So let me look at mode. I have to be in degrees. Window between 0 and 360. In a scale of 30 degrees, so it worked fine. And I don't know what I'm going to... Oh, I just have sine, tangent, cosine, so I might as well go between -2 and 2. That way we get the largest graphs. And, well, maybe that's all right. That'll work. So here we have 30 degrees, 60 degrees. Over here is 210 degrees, 240 degrees. So that is indeed correct. I'm just going to copy this here and paste it into Word. Actually, that might just take too long to put in here. So again, here's 30, 60, 210, and 240 degrees, just as it had said. Actually, put it right there. Okay, the second one then. Okay, we have tangent of 2 theta plus 1, because that's at -1 on the other side. So I'm going to graph. Okay, there's one solution. There's another one. There's a third. And there's a fourth solution. And again, I copy that. Go back to Word. Insert it. So there we go. And the solutions that we come up here are just beyond 60 degrees. And then this one here is just beyond 150 degrees. And this one is just beyond 240 degrees. And this one is just short of 360 degrees, just like it said the solution should be. And one more to do to check with the graphing calculator. This time around it's a little slower because I keep getting them in one at a time. Cosine 3x plus 1. Let's see what we get when we graph. Okay, just touching there. Yeah, that makes sense. Exactly pushed up by 1. And we can see that we have solutions here of 60 degrees, or actually let me again copy this one. Go back to Word. And here we go. And as we can see, 60 degrees, 180 degrees, and 300 degrees are indeed the solutions. Okay, let's go on to the next example or problem. It says, find all solutions between 0 and 2 pi. Use exact values only. So we're going to look at sine 2x, cosine x plus cosine 2x sine x equals 1/2. Well, that looks like sum or difference formula. So I'm going to look in the tables beginning or end of the book, and the sine, cosine plus cosine sine goes with sine A plus B. So I'm going to come up with sine A plus B equals 1/2, respectively. Sine 2x plus x, of course, comes out to 3x, and that equals 1/2. Of course, that's why they gave us a problem, because here again we have a multiple angle in there. So we're going to come up with 3x equals, we're supposed to go all the way to 2 pi for the x, but because of the 3 here, again, we can go all the way up to 6 pi. And then, of course, once we have divided by the 3 here, we're back to the required 2 pi. So again, keep that in mind. So 3x is going to be 1/2, of course, puts us at 30 degrees and 150 degrees. So pi over 6. And 5 pi over 6. But then, because we're allowed to go all the way up to 3 times 2 pi, so all the way up to 6 pi, or 1,080 degrees, I just noticed that I chose a different kind of problem. That's okay. This works perfectly fine here. Just back up here. I may want to switch this one here. This was not 26. This is 25, and then I want to do 26. You will see that in the notes when you have them printed. I was just looking at the solution manual and noticing, oops, a little bit off. In any case, I didn't make a single mistake here. So 5 pi over 6. Then, so we have 30 degrees, we have 150 degrees, then we have 390 degrees, which is going to be 13 pi over 6. I should just copy this one here. 13 pi over 6. And then we're going to have 17 pi over 6. And then we're going to have, let's see, 750 degrees. So we're going to have, let's see, that's 12, 6, 24, 6, I believe it's 25 sixths. So 25 pi over 6. And then we're going to have 29 pi over 6. And then we divide by the 3 here, and therefore each of these here is going to take on 18. This will take a while here. 18, 18, and so on. And those are indeed the correct solutions. Okay, this one here, obviously the same kind of sum formula. So we're going to come up with sine 3x equals -1/2. Our solutions this time around would be kind of similar to these here. But of course we're going to be in the 3rd and the 4th quadrant, so we're going to be at, first of all, at 210 degrees, which puts us at 7 pi over 6, and after dividing by 3 we come up with 18, and then this one here is putting us at 11 pi over 6 divided by the 3, and then this one here will be 12 plus the 7, which is 19. This one here is 12 plus the 11, which is 23. And this one here is 24 plus 7 is 31. And this one here is 24 plus 11, which is 35. And again, you can check these solutions. One last example problem for this one here. The formula below, so this formula L equals 2R sine 180 degrees over N, and notice that this one is inside the sine, is the relationship between the number of sides N, so 1, 2, 3, 4, 5, 6 in our example here, the radius R, and the length L of each side in a regular polygon. Find N, that means find the number of vertices, and that's also the number of sides. So determine what kind of polygon it is if the side L equals the radius R. We pretty much can say that, well, if that's the case, the drawing already gives it away. We're going to have a polygon with 6 sides. And of course, it would make sense that if radius, this is the radius, and that's also the radius, and then the sine is the same length, of course we need a 60-degree angle here, and then the center, we have to come up with 360 degrees, and of course, we can only do that if we do 6 of these equilateral triangles. In any case, they want us to do this algebraically. So we have L, side L equals R. So that actually cancels out. For example, if this one here is 5 and this one is 5, then the 5's cancel out. And what we have then is, so we divide by L over R, and we have 1 equals 2 times 1. Of course, we don't need to read that, times the sine of 180 over N. There we go. And so here we're going to have sine of 180 over N equals 1/2. What are the solutions to that? Respectively, this of course is going to give us, as a reference angle, 30 degrees. So 180 degrees over N is going to give us 30 degrees after we have taken the inverse sine. And then, of course, N comes out to 6, just like we had said a moment ago. But as I said, we were supposed to show this algebraically. One other thing here, this one here, another solution to it, of course, would be that we come up with 150 degrees. So this here potentially could be a solution. 150 degrees being in the second quadrant. But then we get a fractional N of, I believe, 6 over 5 or 1.2, and we need an integer number because the N is the number of sides and it can only be an integer number of sides. So this solution here wouldn't work. And with that, I conclude the problem section for trigonometric equations involving multiple angles. And as you noticed, the problem section as well as the lecture, they were kind of complementing each other. So I did a little bit different here and a little bit different there.